So, uh, picture a war room for a second.
Okay.
You're looking at this massive screen, right? And global temperatures are just ticking steadily upward, crossing all these critical thresholds. Crop yields are dropping. Heat waves are just completely stalling over major cities.
A total worst case scenario.
Exactly. And then, without any warning, no international consensus, nothing. A single official in one really highly impacted nation, just they press a button.
Right.
And suddenly, fleets of these high-altitude jets take off. And their sole task is spraying thousands of tons of sulfur dioxide straight into the stratosphere. Like, the goal is literal here. Block out a fraction of the sun to artificially cool the Earth.
Yeah, it's a unilateral, totally uncoordinated decision to basically hack the climate.
Yeah.
I mean, it sounds completely like science fiction, but you have to understand the physical mechanisms to do this, the planes, the materials that exist right now.
Right. And the problem historically hasn't actually been the planes or, getting the sulfur. The problem has always been the math.
Oh, absolutely. The math is a nightmare.
Because if one country just starts spraying aerosols, to even guess what happens next, like who gets devastating droughts, who gets sudden floods, or, whose monsoon season completely fails, you would typically need this massive, warehouse-sized, supercomputer crunching atmospheric data for, like, months on end.
Which means, practically speaking, by the time you actually figure out the geopolitical fallout of that deployment, the climate's already shifted. It's too late.
Exactly.
But we are actually looking at a massive paradigm shift today, because that entire uncoordinated geopolitical nightmare, it can now be simulated and gamed out in seconds.
Seconds.
Yeah, on a standard laptop.
Which is just wild to think about. So welcome to this deep dive. For you listening, the learner in our mission today is exploring a 2026 technical paper from Geoscientific Model Development.
A very dense paper, I might add.
Super dense. We're looking at the mathematical architecture of this brand new tool called CIDER. That's the Climate Intervention Dynamical Emulator.
Right.
And this paper, it just completely changes how researchers map out global geoengineering. So to really set the stage for you today, I want you to imagine the virtual backdrop behind us shifting right now. Like, gone are the usual studio walls. Instead, just picture this glowing digital projection of the Earth. And it's crisscrossed with real-time data streams, stratospheric wind patterns, and, high-altitude flight paths.
I love that visual, because we really do need that global perspective here. We are unpacking what is essentially the ultimate simulation tool.
Yeah.
And to understand why CIDER is such a massive breakthrough, we really have to look at the sheer overwhelming complexity of stratospheric aerosol injection, or SAI.
Right, the aerosol spraying.
Exactly. It's a specific type of solar radiation modification. You inject aerosols into the upper atmosphere and they scatter incoming sunlight. This increases the Earth's reflectivity, its albedo, and offsets the warming caused by greenhouse gases.
But the catch is that the Earth's climate is this deeply coupled, completely chaotic system.
Oh.
You don't just, walk up to a global cooling dial and turn it to 10. You have to make these highly specific choices, and every single choice triggers a totally different butterfly effect.
Right. In modeling, we actually call those choices degrees of freedom. So if you want to deploy SAI, you have to choose the exact latitude of your injection.
Like where the planes are flying.
Exactly. Are you flying jets at, say, 60 degrees north to target just the Arctic, or 30 degrees north, or maybe right at the equator?
Wow, okay.
And then you also have to choose the magnitude, like how many millions of tons of sulfur are you dumping? And the timing, the temporal evolution, meaning how does that injection scale up or down over decades?
Right.
Every single combination of latitude, magnitude, and time creates a completely unique global weather response.
Okay, let's unpack this. Because if a policy team wants to simulate all those different choices using traditional Earth system models, and these are behemoth programs, right? Like CESM2, CCM6, or the ACCM6. It is just incredibly punishing computationally. It's like, okay, it's like trying to figure out what happens if you add a new stoplight to a busy intersection. But to test it, you build a hyper-realistic, life-sized, fully functioning physical replica of the entire city.
Yes, that's exactly it.
And you track every single pedestrian and every car for years just to see if traffic backs up. I mean, it is unimaginably expensive.
You'd spend your entire computational budget just running maybe one or two scenarios. But CIDER, on the other hand, is an emulator.
Okay.
It operates as this highly sophisticated shortcut. It trades a tiny, carefully calculated bit of fidelity for a massive, massive increase in speed.
So it skips building the city.
Right. Instead of calculating the physics of every single cloud formation and wind current from scratch, it uses reduced complexity modeling. So it can predict temperature, precipitation, and evaporation in literal seconds.
That's incredible. And the paper actually breaks down the engine undersider's hood into 4 distinct mathematical steps.
Yeah.
Let's look at how it actually gets from, spraying sulfur from a jet to predicting global rainfall.
Yeah, let's get into the math.
The first hurdle is just translating the physical spray into an atmospheric haze, right?
Correct. The model starts with a time series of the injected sulfur dioxide and translates that into what we call a global mean aerosol optical depth, or AOD.
AOD.
Okay, basically it's a measure of how thick the haze is, and it does this using the convolution of impulse responses.
Okay, I want to pause on convolution of impulse responsive because that is some heavy mathematical jargon.
Fair enough, it is a bit dense.
The way I visualize an impulse response is like striking a tuning fork and measuring the ringing as it fades out over time, right?
Mm-hmm.
It measures how a system behaves after a sudden, really sharp input. But convolution means you aren't just striking it once. If you're continuously spraying aerosols year after year, you are striking new tuning forks while the old ones are still ringing.
That is a great way to put it.
So convolution is basically the math of adding up all those overlapping echoes to figure out the total noise level in the room at any given moment.
That captures the dynamic perfectly. And the researchers actually determined these impulse responses by looking at massive sudden inputs. Specifically, these 35-year step injections of 12 teragrams of sulfur dioxide per year.
Wait, 12 teragrams. Just to give that number some real-world context for you listening, the 1991 eruption of Mount Pinatubo in the Philippines blasted roughly 15 to 20 teragrams of sulfur dioxide into the stratosphere.
Right.
And that single event cooled the entire planet for a couple of years. So the researchers are feeding CIDER data equivalent to a near Pinatubo level event happening continuously every single year.
Every single year, yeah. Just to see how the mathematical tuning fork rings, as you said.
Wow.
And once CIDER calculates that overlapping global haze level, the AOD, it moves to the second step. It calculates the global mean climate changes.
Okay, how does it do that?
Well, it takes the overall cooling from the aerosols, pits it against the overall warming from accumulated greenhouse gases, and then it feeds that net energy change into a semi-infinite diffusion model.
A semi-infinite diffusion model. Let's break down the physical mechanism there, because the Earth isn't just a flat surface that heats up and cools down instantly, right?
No, not at all.
The oceans are incredibly deep, and they act like this massive thermal sponge. So semi-infinite in this context means the math treats the deep ocean as a seemingly bottomless heat sink.
Exactly.
The model calculates how heat slowly diffuses down through the layers of the ocean over time, or how the ocean releases heat back into the atmosphere if the surface suddenly cools down from the aerosol haze.
And that is vital for capturing the lag in the climate system. Because of that ocean heat sink, if you block the sun today, the Earth doesn't reach its maximum cooling tomorrow.
Right, it takes time.
Exactly. The semi-infinite diffusion model accurately mimics that decades-long thermal drag. So now, after step 2, CIDER has an accurate prediction of the global average temperature change.
But I mean, a global average is functionally useless for a regional policymaker.
Oh, completely useless.
Like, knowing the planet cooled by 1 degree overall doesn't tell you if it's freezing in London, or if the monsoon failed in India, or if Brazil is experiencing a mega drought.
Which is exactly why we need step 3, pattern scaling. The team took these highly detailed 2D spatial maps that were generated by those massive supercomputers for single latitude injections.
Right.
And CIDER takes those pre-existing maps and mathematically scales them up or down. So if the global diffusion model in step 2 says we have a lot of cooling, CIDER just intensifies the colors on that 2D map.
Got it. And then the final step, step 4, is where things sound almost like too simple to actually work.
It really does.
CIDER takes all those scale 2D maps from the different injection latitudes and just adds them together to get the final global weather map. So you inject at 30 degrees north, you inject at the equator, you scale the 2 maps, and you just layer them on top of each other.
Right. It assumes the climate responses are entirely linear.
So you have to challenge this premise.
Because the Earth's climate is literally the poster child for massive, chaotic, nonlinear dynamics. The butterfly effect dictates that one small change alters the entire system unpredictably.
Yeah, that's the standard thinking.
Right. So if you have 2 different aerosol clouds shifting atmospheric winds at the exact same time, shouldn't they interact and create completely new weather patterns? Wait, You're just adding complex weather patterns together, like
Right.
layering different colors of paint on a canvas. Doesn't the Earth's climate have massive chaotic butterfly effects where 1 plus 1 doesn't equal 2?
What's fascinating here is that that intuition makes perfect sense when you look at local day-to-day weather.
Okay.
But what the researchers rigorously proved is that for large-scale, long-term climatological variables like decadal temperature averages or seasonal precipitation across a whole continent, the assumption of linearity actually holds up remarkably well.
Really?
Yeah, they ran the complex, fully interacting simulations on the supercomputer, and then they ran the simple linear addition on CIDER. And the large-scale output maps were nearly identical.
Adding the patterns linearly works because the massive scale of the atmospheric response just smooths out the local chaotic weather noise. They trained CIDER using those 35-year step injections of 12 teragrams to prove that these individual patterns can indeed be combined accurately.
So, as long as you're looking at the big picture over years, the linear shortcut is actually incredibly reliable.
Exactly.
But the paper itself admits that this linear assumption eventually hits a brick wall. Like, there are elements of the Earth system that do not smooth out. And the most glaring exception they had to solve for is sea ice.
Right, because unlike temperature, which can theoretically just keep shifting up or down forever, sea ice is a strictly bounded physical problem.
It has limits.
Exactly. It exists on a hard scale. It's represented as a fraction between 0, meaning open ocean, completely ice-free, and 1, meaning solid, unbroken ice. You can't have a prediction of negative 20% ice coverage, right?
Right.
Nor can you have 120% coverage.
Yeah. And more importantly, ice doesn't melt in a straight linear line. If the temperature goes up by 1 degree, you don't just lose 10% of the ice and then another 10% for the next degree.
No, the physics don't work that way.
Right. It's dictated by the albedo effect. Solid white ice reflects sunlight, keeping the area cold.
Mm.
But once it starts melting, it exposes dark ocean water.
Mm.
And that dark water absorbs solar heat aggressively, which melts the surrounding ice faster, which exposes more water, which absorbs more heat. It's this runaway feedback loop.
It is. And to capture that sudden compounding collapse in the Arctic, the researchers had to build a novel statistical extension specifically for CIDER.
How did they do that?
They divided the entire Arctic region from 60 to 90 degrees north into 24 distinct geographic domains by longitude and latitude.
Okay.
Then they fit a specific mathematical curve to each individual grid cell within those domains based on regional temperatures. They used a logistic function commonly known as an S-curve.
Okay, an S-curve. So what does this all mean? The S-curve actually perfectly mirrors the physics of the albedo effect we just talked about. It's like a tipping point.
Yeah.
Imagine pushing a really heavy box. You push and push with almost no movement. That's the cold temps, the solid ice. That's the bottom flat tail of the S-curve where the ice remains solid at 1.
Right, the white surface is reflecting the sun, resisting the heat.
But then suddenly, the temperature hits a critical threshold. The ice begins to fracture. The dark water is exposed, and it's like the box finally breaks friction and slides fast.
Yeah.
You hit the steep vertical middle section of the S-curve. The ice coverage plummets rapidly in a nonlinear freefall, and then finally the melt hits the wall and stops. That's the bottom flat tail of the S-curve in zero ice, because the ice is simply gone.
That's a great analogy. The logistic function naturally bounds the data between 0 and 1 while capturing that catastrophic midpoint collapse.
Right.
But to make this algorithm function efficiently without throwing errors all over the place, the researchers applied this brilliantly simple filter during the training phase.
Oh, what was that?
They analyzed 444 different time points in their climate data, and they realized that trying to force an S-curve calculation onto a patch of ocean where ice almost never forms like the very southern edges of the Arctic domain, it just breaks the math. It creates mathematical noise.
Well, because the model is hunting for a complex tipping point in water that is already reliably ice-free.
Right.
It's just wasting computational power.
Exactly. So they instituted a cutoff. They simply excluded any grid cell that never exceeded 15% ice coverage during the historical training data.
That makes so much sense.
Right. If the ice isn't substantial enough to begin with, CIDER doesn't bother running the complex logistic function for it. That single filter cleaned up the math beautifully. It allowed the emulator to accurately predict the September Arctic sea ice minimum using nothing but the regional temperature inputs generated by those linear steps we discussed earlier.
Wow. So we now have this incredibly fast tool. It handles linear temperature patterns, it handles the thermal drag of the deep ocean, and it has this dedicated S-curve extension to capture the sudden collapse of Arctic sea ice.
It's a fully functioning digital sandbox.
Which brings us to, honestly, the most dramatic part of the source material. The researchers decided to actually take CIDER for a spin by simulating uncoordinated multi-actor geoengineering.
Yes, this is the scenario that literally keeps geopolitical analysts awake at night. Because CIDER processes data in seconds, it allowed the team to map out what happens if multiple different coalitions or nations decide to deploy stratospheric aerosol injection at the exact same time,
Oh boy.
without ever communicating with each other, and with actively conflicting climate goals.
Okay, let's lay out the board for this global simulation. We've got 3 independent actors. Actor 1 initiates their deployment in the year 2035.
Okay.
They are injecting sulfur dioxide exclusively at 60 degrees north, and their goal is narrow and specific. Cool the Arctic region back down to the temperatures we saw in 2020 to save the sea ice.
Which is a very plausible first-mover scenario, honestly. Polar deployment requires fewer aircraft and less sulfur to achieve regional cooling compared to a whole global operation.
Right. But then, 5 years later, in 2040, Actor 2 enters the arena. They begin injecting massive amounts of aerosols at the equator, and their goal is far more aggressive. They want to force the overall global mean temperature back down to the year 2000 level.
So Actor 2 is basically trying to throw a thermal blanket over the entire planet.
Exactly. Which immediately complicates things, because equatorial cooling will naturally bleed over and lower temperatures in the Arctic, overlapping with what Actor 1 is already doing.
Right. And then, in 2042, Actor 3 begins their deployment at 30 degrees south. Their specific objective is to fix the north-south temperature gradient.
And the temperature gradient is crucial here. If you cool the northern hemisphere more than the southern hemisphere, you actually physically shift the intertropical convergence zone, right?
Yes, that's the band of heavy rainfall near the equator.
Right. A disrupted gradient means monsoon seasons shift geographically, which causes massive droughts in regions that rely on that rain for agriculture. So Actor 3 is spraying in the south to pull that rainfall band back into balance.
So we have 3 actors, 3 completely different temperature targets, injecting at 3 different latitudes. It is total climate anarchy.
Yeah.
Because they are all injecting into a single, shared, circulating atmosphere, they immediately accidentally step on each other's toes without ever talking. As Actor 2 blasts aerosols at the equator to cool the globe, the Arctic begins to get double cooled.
Right, because if Actor 1 keeps spraying at full capacity, while Actor 2 is also cooling the globe, they risk plunging the Arctic into an artificial deep freeze.
Exactly.
Potentially triggering unintended weather disasters across northern Europe and Canada.
And to prevent that overcooling, the simulation shows Actor 1 is basically forced to scale back their high-latitude injections. They drastically drop their injection rate, eventually shelving half of their operational capacity. They keep 4 teragrams of sulfur dioxide on standby, essentially mothballing their fleets, just waiting to see what the other actors do.
So they're forced to adapt dynamically to a rogue global deployment. But the climax of the paper hits in the year 2053.
Right. In 2053, Actor 2 suddenly and permanently terminates their equatorial deployment.
Just stops.
Just stops. The researchers don't script a geopolitical reason. I mean, it could be a massive economic collapse, a domestic revolution, sabotage, whatever.
Right.
The reason doesn't matter to the climate. The injections at the equator simply stop.
Here's where it gets really interesting. Think of this scenario like 3 incredibly stubborn, completely silent roommates who are all secretly hacking the central thermostat of a massive house.
Oh, I love this.
Right. Roommate 1 is in the attic, desperately trying to keep their room freezing. Roommate 2 is trying to cool the entire house by just blasting the central AC. Roommate 3 is in the basement trying to balance the airflow so the room doesn't get stuffy. When roommate 2 suddenly goes bankrupt, moves out, and shuts off the central AC, the house experiences termination shock. The temperature aggressively spikes everywhere. Roommate 1's attic starts baking instantly, so they have to scramble to buy personal fans and window units just to survive.
That is exactly what happens. When Actor 2 terminates in 2053, the global stratospheric haze dissipates in a matter of months, and the suppressed greenhouse gas warming comes roaring back.
It just spikes.
Exactly. Actor 1 immediately scrambles to reactivate that 4 teragram standby capacity to prevent the Arctic ice from melting overnight. And because the sudden termination completely destabilizes the global rainfall gradient, actors 1 and 3 are finally forced to acknowledge each other.
They actually have to coordinate.
Yes, they abandon their individual localized goals and spend the next 5 years desperately coordinating a balanced deployment at 30 degrees north and 30 degrees south just to stabilize the atmosphere. The simulation shows they don't fully achieve equilibrium until 2058.
It takes half a decade of coordinated scrambling just to fix the atmospheric whiplash that Actor 2 left behind.
Yeah.
The narrative is cinematic, honestly. But the true triumph of this paper is the validation of the tool itself, right? Because CIDER generated this multi-layered, interconnected geopolitical crisis in mere seconds.
Exactly. And if we connect this to the bigger picture, when the researchers ran this exact same uncoordinated 3-actor scenario on the highly advanced, incredibly slow CESM2 supercomputer model, CIDER's rapid output matched the supercomputer's results almost perfectly.
That's incredible.
It proves that an emulator can reliably map out the physics of a geopolitical mess.
But, we have to bring things back down to earth for a second. CIDER is a shortcut, and shortcuts miss the scenery. So what did CIDER miss? What are the blind spots?
Right. The researchers are very transparent about where CIDER fails. An emulator is a scout, not a perfect replica.
Right.
And it has distinct blind spots. The most glaring error pattern emerged when they looked at the northern Atlantic Ocean. When comparing CIDER to the full supercomputer models for gradual multi-objective scenarios, CIDER completely failed to capture the dynamics of the AMOS.
The Atlantic Meridional Overturning Circulation.
Yes.
That's the massive ocean conveyor belt that pulls warm surface water from the tropics up to the North Atlantic, where it cools, becomes dense, and sinks to the deep ocean. It basically dictates the climate of Western Europe.
Exactly.
Why did CIDER miscalculate something so massive?
Well, it comes down to the physics of salinity and density and how CIDER was trained. Remember, earlier we discussed that CIDER learned how the climate reacts by analyzing sudden, massive 12 teragram step injections.
Right, the Pinatubo tuning forks.
Exactly. When you drop global temperatures that violently and suddenly in a supercomputer simulation, it drastically alters global evaporation and rainfall patterns instantly. That sudden shift dumps massive amounts of fresh water into the North Atlantic.
And fresh water is less dense than salty water, so it doesn't sink.
Precisely. The surface water gets too light to sink, the conveyor belt jams, and the AMC rapidly slows down, leading to severe localized cooling in the North Atlantic.
Oh, I saw.
Because CIDER learned from those massive sudden shocks, whenever it tries to emulate a scenario, even a scenario where an actor is very slowly and gradually ramping up their deployment over 20 years, it inappropriately predicts an AMOC collapse.
Oh, wow.
It assumes the ocean density is getting violently slammed when in a gradual scenario, it's really just getting gently pushed. The emulator predicts a catastrophic cooling in the Atlantic that wouldn't actually happen.
It's basically applying the physics of a car crash to a situation where someone is just, slowly applying the brakes.
That's a great way to put it. Furthermore, CIDER mathematically inherits the blind spots of whatever parent model it was trained on. For instance, when the researchers trained CIDER using data from the UKSM1 model, it struggled with aerosol nonlinearities at very high injection rates.
Let's look at the mechanism there. If you pump a small amount of sulfur dioxide into the stratosphere, it disperses nicely into a fine reflective mist.
Right.
But if you pump millions of tons into the same latitude incredibly fast, the atmospheric physics change, don't they?
They absolutely do.
The aerosol particles start colliding. They clump together, or coagulate, into larger, heavier particles. And larger particles are less reflective per unit of mass, and because they are heavier, gravity just pulls them out of the stratosphere faster.
Right. The UKSM1 supercomputer model calculates that clumping effect perfectly. But CIDER, relying heavily on its linear addition steps, sometimes misses that coagulation dynamic at the extremes.
I see.
It assumes the cooling effect scales up neatly, meaning CIDER can sometimes overestimate how much cooling a massive deployment will actually achieve.
Okay, but if the emulator has these physical blind spots, like if it's predicting ocean current collapses that won't happen, and overestimating the cooling power of aerosols because it misses the clumping effect, why use it at all?
That's a fair question.
Why not just demand the supercomputer run every single time to ensure you had the actual physics right?
Because the sheer volume of geopolitical possibilities is infinite. You cannot run 1,000 different variations of uncoordinated actors on a supercomputer to see which one causes a famine in South Asia.
It's just too expensive.
Exactly. You would run out of funding and time before you tested a fraction of them. CIDER isn't meant to replace the supercomputer. It acts as a high-speed scout.
A scout.
You use CIDER to rapidly sweep across thousands of different injection latitudes, magnitudes, and uncoordinated termination scenarios. It flags the most geopolitically fragile or dangerous outcomes. And once the emulator has mapped the territory and found those crisis points, then you allocate your expensive supercomputer time to run the high-fidelity physics simulations on those specific critical scenarios.
So it's basically the drone mapping the entire forest canopy before you commit to sending in the heavy machinery.
Exactly.
That makes total sense. Well, let's look at the incredible ground we've covered in this deep dive. We started with the overwhelming degrees of freedom inherent in hacking the stratosphere. We broke down how CIDER uses convolution and semi-infinite diffusion to translate a sulfur spray into a thermal ocean lag. We explored the limits of linear addition, relying on that albedo-driven S-curve to map the sudden collapse of Arctic sea ice. And we watched the tool successfully game out a chaotic, multi-decade thermostat war between 3 uncoordinated actors.
It really demonstrates a remarkable leap in reduced complexity modeling. The physics of global climate intervention can now be translated into rapid mathematics.
And for you, listening right now, the implications are profound. Whether you are actively prepping for a policy meeting or you're just deeply curious about the immediate future of the planet, understanding tools like CIDER is vital.
It really is.
It signals that we have officially moved past theoretical what-if science. We are actively building the real-world logistical architecture to simulate global intervention.
Which leaves us with a very provocative dynamic to consider, because CIDER is computationally light enough to run in a web browser.
Right.
It can be utilized live in the middle of a real-time defense or climate policy workshop. We are actively democratizing the ability to simulate hacking the Earth. And the unresolved question here is behavioral. Does making it radically easier and cheaper for military strategists and policymakers to game out geoengineering scenarios make them more prepared to anticipate and stop a rogue actor? Or does seeing the math neatly balanced on a laptop screen strip away the fear, making them vastly more tempted to actually press the button themselves?
From a warehouse supercomputer to a laptop in a war room, it turns out the faster we can simulate altering the global climate, the closer we might actually get to doing it. Something to think about. Until next time, keep diving deep.